Okay, Navneet, Harshit, and Satvik are there. So, did you guys went through those videos which I asked you to see yesterday?
Sorry, ma'am, I'm not.
Okay, just a minute. Harshit couldn't go through, and we have Satvik. Okay, Satvik, can you briefly explain us what was there in the videos? You are not audible, Satvik. I'm audible, right?
Yes, ma'am.
Okay, Satvik there. Okay, okay, it's okay. Take your time. Take your time.
Hello.
Okay. Meanwhile, Navneet, what about you? Have you seen the videos?
Modeling this as my method of.
Hello.
Yes, Satvik, go on.
Yes, ma'am. The video first started with homophility. I mean,
Okay.
what it is. Then moved on to selection and social influence and
Okay.
how they are related with each other.
Okay. Can you help us understand the difference between selection and social influence and how they are related to homophily? Anyone can answer for as a matter of fact. We are just discussing. Go on, Satvik.
Consider two people A and B.
Okay.
If those two have similar habits, I mean similar personalities, then they become friends.
Okay.
And it is dependent on those two peoples as they select each other.
Okay.
Uh, Whereas coming to social influence, in a group
Hmm.
of friends,
Hmm.
if most of them like to eat out, I mean, like to
Hmm.
uh, go out and eat
Hmm.
regularly, then
Hmm.
the one who doesn't also learns to go out. I mean, he
Perfect.
follows them outside.
Perfect. Exactly. So what Satvik is trying to say that in our social networks, we generally observe homophily, that people who are similar to each other, it is seen that they are also friends with each other. So why does that happen? So even in this figure which you see here, we have two kinds of people, blacks and whites. It's a friendship network. So what you will observe are blacks are mostly friends with blacks and whites are mostly friends with white. Here it's based on the skin color. It can be based on a number of other aspects. And why does this happen? So there are two reasons which Satvik told us. One is the selection, and second is social influence. So selection says that we are free to choose our friends. So whenever we go in a classroom setting or maybe an institute and we have to choose friends, we look for something in common and then we become friends. So maybe you look for similar grades, or maybe a sports you are interested in, or something other, or same club, and then you choose your friends. Social influence is slightly different. So social influence says that it's a correlation versus causation question. So, what social influence says that it might be so possible that A and B, they are not similar in any aspect. So, a body weight is a very good example for this. So, let's consider two people who have different BMIs and they become friends. So, A and B, let's say, just a second. Okay. So let's say A here is a person having a low BMI. On the other hand, B is obese. And because of some other reasons, they become friends, right? So what will happen with time? With time, there is a good chance that A will gain weight because of sharing the same habits as B. So let's say B goes to a coffee shop and eats sandwiches. A also go there and starts eating sandwiches on a daily basis. So with time, A also gains weight, and now A and B becomes similar. So what we will discuss in today's session is less about this selection versus social influence, but more about how do we measure homophily in a network. So some of you might have seen in the video. So we'll dissect it all the more further and think about it more deeply. How do we actually measure whether there is homophily in the network or not? So as an example, if you see in this network, it is very clear here that there is homophily because blacks are mostly friends with black and whites have their own community. So assume that I give you a social network. So let's talk of a simple classroom network where we have boys and girls, and assume that we are interested in seeing that whether this friendship network in this classroom exhibits homophily, in the sense that whether there is this kind of phenomenon that girls tend to become friends with girls and boys tend to become friends with boys, or there is nothing like that. So both boys and girls are friends with each other, and how do we do that? So look at this network here. So assume that these blue nodes here, so I've shown you three networks here. Let's say the blue nodes, they are boys, and the pink nodes, they are girls. So can you now have a look at this network? So the networks which exhibit homophily, we say that they are assortative. So if you see in a network that people who are similar to each other, they tend to become friends with each other, we say it is assortative. On the other hand, if opposite happens, so consider these two classrooms. One classroom in which people become friends with same gender people. So we say that this network exhibits assortativity. On the other hand, if something opposite happens, so that is people tend to become friends with opposite gender people, then we say that the network exhibits disassortativity. So can you look at these three networks and tell me which one is assortative, which is disassortative, and which is neither of these?
Ma'am, first one is authority, ma'am.
Okay,
Second one is uh, uh, ma'am.
first one, Harshit says first one is assortative. Okay. Right. So this one is assortative because if you look at the edges here, so edges are only between either two pink nodes or two blue nodes. So if you never see an edge in this case from a pink node to a blue node, right? So actually in this network there is no intergender link. So you won't see a link between a boy and a girl anywhere. So this network is perfectly assortative. Only similar gender people become friends with each other. Okay. What about this one here? Look at the last one.
Ma'am, it is a neutral, ma'am. It is neither of them, ma'am.
The last one.
Yes, ma'am. Why? Because there are no friends between the girls and girls, ma'am. I
Okay.
think, yeah, yeah.
Okay. Perfect. So let's rather talk about the second one here. You are correct, Harshit. So if we look at the second one here, so in the second case, opposite thing is happening. You won't see a tie between a boy and a girl. So all the ties are either between these pink nodes or between the blue nodes. So we say that such a network is disassortative or it doesn't exhibit homophily. Disassortative. And this one here is neutral. Okay. So we got this. So these networks are very simple. So this one is a small network. And if we look at this network over here, this we visualized in such a way that it was very easy to look at it and tell whether the network is assortative or not. Now, what if I give you a network and the attributes associated with nodes, let's say whether a node is a boy or a girl, and then I ask you, what do you think, whether this network is assortative or not? So how will you actually quantify it and tell me? Anybody have any idea? So it was discussed in the last video. So I'm going to give you a real world network. Let's say a network of your classroom, and in this network, I have boys in blue color, girls in pink color, and you are supposed to tell me whether this network is assortative or disassortative. So how will you go about it? Okay. So let's start with this question here. So assume what if it's a complete network? Let's say I have three boys in the class, just to keep it simple, and I have two girls, and I say the network which I'm giving you here is a complete network. Everyone is connected to everyone else. Let me just right. So this is a complete network on 5 nodes. So what is this complete network? What will you call it? Whether it is assortative or disassortative or neutral. Okay. Navneet says it's a neutral network, right? Because everyone is a friends with everyone, so no one is biased in their friendship. So it's not like boys are saying we'll become friends with boys or we'll just become friends with girls. So you don't see anything in such a network. So it's a complete network, and this one is a neutral one here. Now, what will happen? The network which I'll give you on three boys and two girls, or in general, if we talk about any other network, what will happen? All these edges will not be present there. Some edges will be missing there, and then we have to predict whether it is assortative or disassortative, right? So, what should happen if I take out some edges from this network? Then, in order for this network to become neutral, what should happen? So let's say I classify the edges here in two categories. Uh, Let me say one is your intragender edges. So there are some intragender edges in this network. So which are your intragender edges which run between the same gender. So this one here, this one here, this one here. So these are your intragender edges. And then we have intergender edges. So the remaining ones running from this part to this part, they are your intergender edges, right? So there is some ratio of intragender edges to intergender edges here. You can compute that here. So what is their ratio? So what should happen when I'm taking away from some edges from this network? So in order for the network to remain neutral, what should happen? The edges should reduce in this particular ratio only. Only then it will become neutral. So what I'm saying is, assume that I'm looking forward to create a classroom which has, let's say, equal number of boys and girls, and there are, let's say, 1,000 registrations, right? So in these 1,000 registrations, I have 500 girls and 500 boys. Now, out of these 500 girls and 500 boys, some are going to drop out, some are going to finally join. So in my class, which will be finally there, if I want an equal number of boys and girls, so what should happen for these people who are dropping out? For one boy, one girl should drop out. Otherwise, my ratio will be disturbed. Similarly, let's say I want 4 times more girls. Then what should happen for every boy? 4 girls should drop out. Only then I can maintain that ratio. So what should happen in any network which I am going to get here after the removal of some edges? This ratio of intragender edges to intergender edges should remain the same in order for the network to remain neutral. So what is the fraction of intragender edges here? So let me just write it down as fraction intris. We have 1, 2, 3, 4. And what is the total number of edges we have in this network? 10, right? And the fraction of intergender edges here is 6 by 10. So now any network which I am going to get here, if this fraction for intragender edges is zero point 0.4 and for that of intergender edges is 0.6, I can say the network is neutral. But what will happen if this fraction of, let's say, intragender edges increases? Let's say in the network which I'm having here, this fraction increases to 0.7. right? And this reduces to zero point 0.3, then the network will become more assortative. On the other hand, if this one increases, the network will become more disassortative. Any doubt here? So let's try to exactly quantify it. Uh, okay, no doubts. I thought my question was, did you understand? And you were saying no. Okay, no doubts. So let's quantify it exactly. So for now, we are working with a network having two categories. Let's say there are P number of boys and rather not P, let us say there are M number of boys and N number of girls, right? On these many boys and these many girls, I have a network and I want to see whether it is assortative or disassortative. So for a neutral network, what should be the fraction of intragender edges here? Can you give me an exact expression here? And what should be the fraction of intergender edges? Can you give me the formula here? So intragender edges are going to run from boys to boys and girls to girls. So how many edges can be there between M boys?
I'm
So
MC2.
MC2, right?
Yeah.
Okay. So this is intragender edges for boys. Similarly, I have intragender edges for girls,
Yes,
which
yes,
is
ma'am.
N
And
choose 2,
yes, ma'am.
divided by what should be in the denominator, total number of edges possible,
Yes, ma'am.
which is
N plus NC2.
M plus N choose 2, right? And what is going to be the fraction of intergender edges?
Uh, it will be for the individual, no, ma'am. Uh,
So intergender edges means all the edges which are possible between boys and girls. So how many links are possible between boys and girls in this network? So we are talking about an undirected network here, keep in mind. So let's say I had some three boys here and two girls here, right? So how many edges were possible for every boy? Two. So it is 3 into 2, right?
yes, yes,
So
ma'am.
in this case, it will turn out into m into n by m plus n choose 2.
Okay.
So this becomes your baseline. And now you look at the network which you are given at hand. So these should be your fractions. In case this fraction exceeds, then your network is assortative. In case this fraction exceeds, your network is more disassortative. Okay. So the expressions which we derived here, they are for an undirected network. So if you would have looked at the expressions in the video which I have given you, they will be slightly different. Now how do you get those? So can you modify these formula and tell me how they will change for a directed network? So for an undirected network, we got this one here, right? There will be a small change in this formula if I'm talking about a directed network here. Can you work it out and tell me? So this one over here, this one is for your undirected network. I want to do it for a directed one here. So you should note here, if I have a network, let's say having n nodes, a network having n nodes, so the total number of possible edges here are n choose 2 in case it is an undirected network. What if it's a directed network? What is the total possible number of edges? See, it should be n square or n minus 1 square. Think about it. So let's say I have this network here. It's on three nodes. How many total edges can I have? So this is one possible edge. This is one edge. This is one edge. This is one edge. This is one edge, and this is one edge. Right? So it is six. How do you get this six here? So every node can be connected to n minus one other nodes, right? So if I look at this first node here, it can have a directed arrow to this node here and this node here, and the same holds for every other node. So what happened? This divided by 2 is taken away. So when I have this n choose 2, I have n into n minus 1 by 2. But when I talk about a directed network, it is n into n minus 1. So what will these fractions now become for your directed networks here? So this m choose 2 will become nothing but m into m minus 1. This is the number of total ties between the boys. This n choose 2 is nothing but n into n minus 1 divided by this one becomes m plus n into m plus n minus 1. And here in this case, when we talk about your intergender edges, how many intergender edges are possible? If you see here, it will actually become 2 into m into n. So if I have, let's say, three boys and two girls, right? So this one can have a directed arrow to two girls. This one can have a directed arrow to two girls. This one can have a directed arrow to two girls, right? So each of the boys here can be connected to n girls. So I got m into n from there. Plus, if I talk about each girl, they again can have a directed arrow to each of the boys. So I get a second m from there. So it becomes 2 into m into n divided by again this total number here, m plus n into m plus n minus 1. Right, so these expressions are slightly clumsy. So what we generally do is, whenever we are looking for homophily, we slightly approximate these formula. So what we do, instead of taking m into m minus 1, if m is very large, it becomes of the order of m square. So that's what you will generally see in the books. So in the books, what you will generally see is, if I'm talking about the intragender edges, you can actually approximate it slightly to be as m square plus n square divided by m plus n square. And this intergender edges, it is approximated to m into 2m into n divided by m plus n square. So it's a slight approximation of this version over here, right? And these are your exact formula. So these are the expressions which you would have seen in the video, or which you will generally find in the books.
Ma'am, I have a doubt, ma'am.
Yes, go ahead.
Ma'am, for this, we can. It must be only two types, or there can be the n types, ma'am.
Come again.
Uh, this assortativity is applied only for the two types of the data, or it can be
Uh,
also. It
I'm
can be.
coming there. Definitely, it can be applied to not necessarily. So there can be n types of nodes, right? So it needn't necessarily be just boys and girls. So it can be any other thing. Let's say how many people are like red, how many people like blue. So it can be any number of categories.
No, no, yeah, it's only two like only taking two categories or n number of ma'am. Basically, suppose we can take yellow, green, and violet. The people
Yes,
who like.
we can have k number of categories. So we'll see how we can generalize this formula to k number of categories.
Sure, ma'am, got it.
Okay. Navneet says aren't both the same. So which both are you talking about, Navneet? This one and this one here?
Yes, ma'am. If we simplify the undirected one, we get the directed formula. M choose to N choose to.
Uh,
Both are same, right?
both are same, is it?
If we cancel the twos in the undirected graph formula,
Okay, and what about the intergender one? They also turn out to be the same. So
same.
here probably divided by 2 is cancelled out for the intragender one. Uh, but then intergender one should also remain the same. Okay. Is it exactly the same?
Yeah, exactly the same, ma'am. Undirected and directed ones. Form.
Okay, okay. Okay, then perfect. I didn't think much about that. Okay, if they turn out to be the same, well, huh, they are the same. You are correct. They are the same. Perfect. So the ratio remains the same whether it is undirected or directed. Can you think of the reason why? Why is it happening so? A nice observation here. Because what is happening when we are converting undirected into directed? You see, our number of edges of each type is simply becoming double. Do you see that? So what we are doing is for every edge from A to B, let's say I was talking about undirected case. So I have an edge from A to B. What we are doing now when we are converting it to a directed case, we are just saying that I can have a to B and back from B to A. So we are just multiplying 2 with we for one edge in undirected, we are having 2 edges in directed one. Right. So it's simply getting double and that is getting cancelled out. Perfect. They are the same. Okay. Uh, So we are going to work with this one here, right? Which are our approximated formula here. Everything clear? Any doubt till here? Okay. Let's come to the question which just Harshit asked us. So what if I have k types of data? So not just 2 types, boys and girls. I have K kind of categories. Can you give me an example here? Let's say it's a university and I'm looking at different nations. Or let's say I'm looking at different cultures or different castes or different regions. It can be anything. So let's say it's different regions in India and we are looking at an institute. Every student is attributed by the state or the city he came from. Let's say the state he came from, and we want to see whether this state has a role to play in the friendships of these people. So whether people tend to become friends if they are from the same state or not. So how do you quantify that? So let's say we have k states we are working with, and then we have students. Let's say there are and one number of students from the first state and two number of students from the second state, so on and so forth, and k number of students from the kth state. So how do I build this formula now? Let's talk about the fraction of intrastate edges. So it can be any category, not necessarily states. Can you tell me this formula, the approximate one? So intrastate edges can be these people which are in N1 state, they become friends with each other. People who are in N2 state, they become friends with each other. So it will be going to be N1 square plus N2 square, so on and so forth up to Nk square, right? And what comes in the denominator? Total possible number of edges, which I am going to write as N1 plus N2 up to Nk whole square, right? This becomes summation I ni square divided by summation I ni whole square. Right? So in that case, you calculate your fraction of intra-category edges like this. And what is the fraction of interstate edges? So for this one, you'll have to slightly think. Can someone tell me the expression for this here? So how many edges can run between the people from different states? So from N1 to N2, N1 into N2, from N1 to N3 it can be, then similarly N1 to N4 it can be, so on and so forth from N1 to Nk. Plus, so this was the relationships which people from N1 state can have with the people from different states. Same for N2, N2 N1, N2 N3, so on and so forth, N2 Nk plus Nk N1, Nk N2, so on and so forth, Nk minus 1. Right? So how do I write this? So I'm going to write this one as, let's say, summation of I comma j, and I should not be equal to j and I and j. Right? So for every two possible pairs of I and j where they are not equal, I'll take Ni and j. And I and j, they both range from 1 to k. And then you can divide it by this expression over here. So this entire thing will be divided by summation I and I whole square. Okay. Can you now try to work out this example? So this is a data. This is the data of sexual relationships in a university. So on the rows are the men, columns are the women, and what it tells you how many relations are there from black to black, then from black to Hispanic, black to white. So we have three categories here, right? So it shows that from black to black we have 506 relationships. From black to Hispanic we have 32, which is not the same as from Hispanic to black, which means it's a directed network. And the number of each kind of edges is given to you. Can you work this out and tell me whether this network is assortative or disassortative? So do it using a pen and a paper. You can use a calculator, and once done, you can take a snapshot of that and put it in the chat window so that all of us can see. If you have any doubt, feel free to ask me. Okay, let's do one thing. I'll leave it as a homework exercise. So I'll give you these slides and you work it out. Meanwhile, I have a few more things to cover. So let's look at them. Okay. Uh, so Harshit raised a nice question. He said, what if we have more than one category? And then we look the example for what if I have K categories? What if I have three categories? Or what if I have four categories? But what if this attribute which I have uh, is not discrete, but it has a continuous value? So let's say I'm looking at whether people make friendships based on their weight. So weight can be any number, it can even be in decimals. So it will be very difficult to quantify such a number into categories. There will be an enormously large number of categories. Or let's say I want to see based on age, where age can range from 1 to 100. In that case, the data will turn out having 100 categories. Right? So is there another way to do this? Let's say for certain attributes which can have a real value. So in that case, how do you measure assortativity? So there's a slide.
Ma'am,
Yes, go ahead, Harshit.
for each category, we can find the variance, mean, median, and we can give them an we can give them a name or something like that, ma'am.
Okay, so my question is, the data is such that it is very difficult to divide it into categories. Let's say the data is regarding the age of a person where it is the exact age. So generally we say my age is 26 or 27. But let's say I'm saying my age is 26.2. Someone is 27.35. Let's say it's weight and not age. So for such a data, something can be 28.66667. How many categories will you make? Let's say if all these real numbers, they vary from 1 to 100, let's say. So these are
Here
all
the
the real numbers from 1 to
okay, ma'am.
100.
Ma'am, here one is a suppose is a category, no, ma'am. Here, by assuming one is a category.
Okay, let's say 1 is a category, fine. So 1 is a category. What is the
Okay.
other category?
Uh,
1.1.
no, ma'am. Basically, means we can take the which has a more repeated, ma'am, range.
Okay, so one
Means the
idea
zero point
maybe
0.2 or 0.5 like that we can check and we can take that in interval.
okay, and what if you do not have the data beforehand? Let's say you need to apply it to 50 odd colleges. So how will you define these categories beforehand? And again, these categories will be different for different networks.
Okay, ma'am.
So one idea definitely which comes to my mind from what you said is we can bucketize them. So we can say, let's say if it is anything between 1 to 2, you keep it as one category. Anything from 2 to 3, you keep it in another category. Right? So you can even reduce the number of categories using that. So let's say 1 to 10 in one category, 10 to 20 in one category. So that way you can reduce the number of categories by bucketizing them, and then you can do your analysis. There is another way to go about this, which is more generally used, and the way is, so see, whenever we are talking about assortativity or homophily, we are concerned about whether similar people, they tend to become friends or not. So what will happen? Let's say a network, if it is let's say demonstrating assortativity, it has assortativity, and I'm in that network. So if you look at all my neighbors, all my friends, their attribute value should be more or less similar to mine. Let's say in a network, I'm looking at whether it is age assortative or not. So you look at all of my friends, so their age should be somewhere be similar to my age. So what we can do is, for every single node in the network, so take one node, look at all the neighbors of this node, right, and take an average of their ages, right, and then you plot this curve. So what the curve will be, here I'll have the attribute values of nodes, so which can be age in this case, right? So for every single node, I'll have an age here. So some node can have an age 1, some has age 2, 3, 4, some have age 100. What I'm going to put on the y-axis is the average age or the average attribute value of their neighbors. And then you look at this curve. Now assume that I'm looking at this plot here and I get three types of curve. Let's say this is my first curve, right? And say this is my second curve. Second, this one is first. And let's say this is my third curve. So now can you think and tell me, so which of these curve demonstrates assortativity, which demonstrates disassortativity, and which is like a neutral one?
Ma'am, three is assortability, ma'am.
Come again, Harshit.
Ma'am, three is assortability, ma'am. One is neutral. Two is opposite, ma'am.
Perfect. I have Satvik, Navneet, and who is the other person? Ali. Right, right. Is it clear to everyone how Harshit answered? Navneet, Satvik, Ali. So what is happening here? If you look at this third curve here, so as the age of a person increases, the average age of his neighbors is also increasing, right? So it is a perfectly correlated curve. So hence we can say that this kind of a curve is nothing but it demonstrates that a network is assortative. On the other hand, opposite happens. So as the age of a person is increasing, what is happened? The average age of his neighbors is decreasing. So it means that let's say here is someone got this problem with this device. Okay, let's say here is someone and this person has an age of 70, let's say, and when you are looking at the average age of his neighbors, it is turning out to be 30, right? Then this network is disassortative. On the other hand, if I have a constant curve, it means that doesn't matter. So the average age of your neighbors is almost carries the same value. It doesn't depend on your age. Then we can say that this kind of a network is neither assortative nor disassortative.
Ma'am, this technique is only used to find the assortability. No, ma'am.
This
This method
uh,
basically plotting like this graph, correlation graph.
correlation graph. Yes, exactly.
Okay.
So it's just means this kind of a plotting you can use it for a number of other factors, but this plot is also useful for looking into assortativity. It's just that we are seeing a plot between person's attribute and his neighbor's attribute, and definitely if they are correlated, the network is going to be assortative.
Yes, ma'am, got it.
Okay. So there is much more to assortativity. So actually assortativity is what gives rise to homophily, and this is what leads to communities in our network. So the people who are similar to each other, they tend to become friends with each other, as you see here in this network over here, right? So what has happened in this network? You can see that there are two communities in this network. So this is a broad field of area which is called community detection. So assortativity is like the very fundamental principles how you start looking into whether a network is having communities, it is assortative or not. So there are more complicated formula here, refining this formula all the further, and we'll talk about that when we'll talk about community detection in detail. So now let's slightly move forward. So what we have done till now, we have looked at certain properties of our real world networks. Right? And what are those properties? Can you briefly remind me? So from the last 2-3 sessions, we have been looking at the characteristics of real world networks. So which are the major characteristics we talked about? So one is assortativity, which we just talked about. Before that, we talked about triadic closure or clustering, right? Which says a friend is back a friend of mine. And what else? We talked about average shortest path length. Average shortest path length was what? So we call that this came from our 6 degrees of separation, which tells that people are close together in a network. It is easy to go from one part of the network to another within a limited number of hops. Okay. So now looking at these properties, what we'll try to do is we have looked at certain properties. Now we'll think about how do I create a network model which has these properties. Assume that I now told you some properties of real world networks, and now I want you to come up with an algorithm to create a real world network. So how will you go about that? So I'm telling you, okay, I have a classroom on, let's say, 100 students, right? So there will be 100 nodes in this network. How do you place edges between these 100 nodes such that whatever network you get at the end has these properties? Let's even forget about the properties in the very beginning. So let's say that I want you to give me the very first model which come to your mind when you have to create a network given certain number of people. Let's say I have some 10 people here. Can you give me a very simple algorithm to put some edges here so that this network looks like a real world network? So one idea you might say, okay, ma'am, connect every node to every other node. Then I know that no, this won't work out. This will become a complete graph. So our real world networks, they are not complete graph. Rather, we have seen that they are sparse graphs, not dense. So they have very limited number of edges. So I'm going to have a limited number of edges in this graph. But how do I place those edges? One idea can be to just create a cycle out of this, right? But again, we know that a real world network probably doesn't look like a cycle. So do you have any other ideas? How should I put the edges here? Any very first thought which comes to your mind?
Ma'am, we have only this information, ma'am. Suppose I'm asking only 10 edges, sorry, 10 notes. Other than
So
we don't
right,
have anything.
yes, other than that, we don't have anything. So right now, we do not have any information about the attributes of these node or anything else. So you can actually even remove assortativity from picture. Uh, So what I'm saying to you is you have looked at various real world networks, right? The Facebook network, the Karate Club network. We have also seen a few properties of this network. So you can even forget about the properties now. Uh, so can you just tell me some way to put some edges here? So right, most in most of this course, we'll focus more on the structure of the network, because
Okay.
whenever you get this data, even the online data, so most of the time you won't get the attributes associated with the nodes. So most of the time what we'll be looking at is the structure of the network. So can you tell me some way of putting the edges here so that this network looks a bit like a real world network and doesn't look like a very good graph theoretical network which is very well organized?
Ma'am, by forming a simple known graph, like a telephone graph or that first question, the bridge problem, like that.
Okay. So do you think that our real world networks are like this? So definitely bucket brigade network is nothing but a path graph, right?
Yes,
Where
ma'am.
people are connected like this. So let's say I'm talking about, okay, Harshit, give me an algorithm which creates a network which is like a Facebook network. So do you think a Facebook network will be something like this?
No, ma'am, but for starting point, we can assume that,
Okay,
no?
for a starting point. Okay.
Yeah,
Okay, perfect.
yeah.
Okay, so Harshit gave me two ideas. He said, okay, maybe we can form a line between them, or maybe we can arrange them in a tree-like structure.
Randomly with connected, somewhat empty, like this.
Yes, so this word which you just now said, randomly connected, right? So I do not know what this network will look like. Why don't you put some random edges here and there? I do not know. Anyone can be connected to anyone else. So the network is not much organized. There is going to be a lot of noise. So why not include some randomness, right? So put some random edges here. How do I place some random edges here? So the very first algorithm, what it says here is to put the random edges. I know how many possible edges are there in this network. 10 choose to, right? I have 45 possible edges. So what I'm going to do is, so let's say this is my first edge possible, this is second edge possible, this is third edge possible. I randomly want some of these to be there in my graph and some of these not to be there. So what I'll do, for each of these edges, I'll toss a coin. If I get a head, I'll put an edge between them. If I get a tail, I don't put an edge between them. And the network which will be generated will definitely not look an organized network. It will be a random network. So we have 5 minutes left. So I leave you with this activity. So it's a very interesting activity. All of you do this. So just chart these 10 notes on a paper. So have these 10 notes. Right? So I have 45 possible edges. Actually take a coin in your hand and flip it for every edge. If you get a head, put that edge there. If you get a tail, don't put an edge. So for the first edge, let's say I got an head, I put a 1, 2, 3, 4, 5. So from 1 to 2, I want to see whether there is an edge or not. I tossed a coin, I got a head, I placed an edge here. 1 to 3, I got a tail, didn't place an edge. 1 to 4, I got a head. So again, put an edge. 1 to 5, put an edge. So on and so forth. So do it for every possible edge in the network. So there will be 45 edges. So toss a coin 45 times. Create this network. So this is our very first algorithm. So what we'll do in the next class, we'll look at the properties of this network. So this was the very first algorithm which was proposed by two scientists named Erdos and Renyi. So these graphs are also called Erdos-Renyi graphs. So generate an Erdos-Renyi graph. So each of you do that. And what we'll do in the next class, we'll look at the properties of that graph. So which properties of that graph are similar to the real world networks, which are not. Okay. Any doubt till here, you can ask me. Okay, and one little announcement for the Friday's class. We again have a faculty meeting. So in the Friday's class, we are going to have presentations from your side. So as I told you earlier, on your very first paper, right? Uh, so Friday, we want have a class from 3:30 to 4:30. So either we can have a class on Friday 7 for your presentations, or we can have it on Saturday at 10. So tell me, which one do you prefer?
Ma'am, for me, Saturday, I think I have a class, ma'am, 9:30 to 10:30.
Okay.
Uh, on Friday, I have no class, ma'am, other than this. So, Friday will be good, ma'am, for me, anytime.
Okay, so Navneet also says Friday, Satvik also says Friday. Okay, so Friday works for everyone. So we'll meet on Friday, 7 p.m. and we'll have presentations from your side. I
Okay,
think
ma'am.
we have how many teams we have? So Satvik and Navneet are together one, and then we have Harshit, and then we have Raid and Shagufta. Three teams, right?
Yes,
So each of you
Vamshi,
can,
ma'am. I think Vamshi
uh,
also.
sorry, Vamshi also. So we get four.
Yes, ma'am.
Right, so each of you can give a 20 minutes presentation at max, so make it anywhere between 15 to 20 minutes. And if you have
Ma'am,
any yes, Harshit, go
ma'am,
ahead.
regarding presentation, what we have to present exactly, ma'am? The paper
uh,
review, or how we are going to proceed with the project, or
Harshit, I couldn't hear the first part of you, what
yeah.
you said.
We have to discuss the paper in the presentation,
Okay,
means
so the
slide.
plan is for now you describe the very first paper. So the basic paper which you are, what I would say, the paper from which you felt motivated, explain that paper to your level best which you can do. So definitely there can be certain points in methodology and literature review sections which you might not understand. That's fine. We'll discuss them over time. So just present that first paper. What we'll do then? Uh, you read some related papers in the next 1 or 2 upcoming weeks. So after you go through that paper from where you felt, which was your motivated paper, and then from those remaining papers which you read as literature. So before this, we are having your what this first minor, no? So immediately before first minor or after first minor, we'll have a presentation where you will clearly define what you are going to do in your project with a Gantt chart with the proper timelines. So I'm giving you some time to read this paper, the first paper and the associate literature, and fine tune your ideas and make a clear mind of what exactly you are going to do. Is that okay?
Yes, ma'am, got it.
Okay. Okay, then we'll meet on Friday 7. And by the way, all of you have seen that I have updated that Excel file with all the lecture videos and the reading material. So you can refer to that reading material for whatever we are studying in the lectures. You can go through those slides and the book, and if you face any doubt at any place, you can let me know.
Sure, ma'am, sure.
Okay, then see you all at 7 on Friday.
Bye, ma'am. Thank you.
Bye, everyone. Take care.